Yeah, thank you. Hello, everyone. Hope you have lunch. And in this section, I just want to recall what we have learned in the morning session, right? So it is very important to see oftenly certain concepts which otherwise forgotten. So this is easy to understand and easy to forget. Therefore, it is better to know more and more time. And whenever the question is asked by the teacher, your teacher, don't ever think that I have not read this. Only after reading I will give a test. It is not so. There will always a scope for making better. What I mean is, you start thinking in a structured way, then definitely you will able to do that well. Right. Now coming to this morning, I have talked about the named reactions and asked a few questions also. Some of you might have answered and some of you might have not answered. If suppose you have not answered, just start telling what is the name of this particular reaction. Okay. Clue number 1. This is from haloalkanes and haloarenes, right? Of course, whenever this is there, you can able to see that silver fluoride is the reagent. Silver fluoride is the reagent, and Br is converted into F. That means fluoramides are converted into fluorides. So this is Schwarz reaction. This is Schwarz reaction, right? Okay, right. Now, this is Schwarz reaction. Now coming to this named reaction. Which is the named reaction? So this is sodium alkoxide and alkyl halide to give ether, right? As I told you, this is Williamson synthesis. This is Williamson synthesis, right? Now, probably you can able to see amide RCONH2, bromine in NaOH will give you amine Na2CO3, NaBr and H2O. Okay. Initially, remember about this amide to amine conversion. And here this CO is being lost. It is something degradation. This way we have to link. And remember, this is Hoffman's bromamide degradation. Well, then, what about this reaction? It is from phenol chapter, alcohol, phenol, and ether chapter again. So, phenol is converted into salicylic acid. Okay. So, this is Kolb's reaction. Kolb's reaction. Yes. Okay. Okay. Well, now, this is the one I have not asked in the morning. Probably that was asked in the morning also. Now, this is the one. So, this way of writing is either aldehyde or a ketone. So, simply they write C double bond O. Because C double bond O is present either in aldehyde or ketone, right? So, this gives a hydrocarbon ZnHgHCl, zinc amalgam HCl. So this is reduction. CO, oxygen is removed and hydrogen is added, right? This you have to observe. So this is Clemenson's reduction. So aldehydes chapter, aldehydes, ketones, and carboxylic acid, this chapter, there is Clemenson's reduction and Wolff-Kishner's reduction, right? And among that, this is ZnHgHCl. Using this reagent, if you are reducing, then it is Clemenson's reduction. There is one more, RNH2, CHCl3, and KOH, giving rise to RNC, a typical compound, RNC, which is of offensive smell. Offensive smell. This is offensive smell. Okay, you want to cut your nose when you inhale this compound. That much offensive smell it has. So this is a carbylamine reaction. This is also called as carbylamine. This itself is called carbylamine. This carbon is attached to NH2. Suppose if there is NH2, hydrogen is replaced by carbon, then it becomes carbylamine. So this name itself is the name of the reaction, carbylamine reaction. Okay, so this is the way you should link to some extent with the product or reactant or the reagent used, and remember. That is only the shortcut way of remembering the named reactions, right? Now, this is a little, the questions will be asked like this. Explain Hell-Vollard-Jelinski's reaction or Wood's reaction. Then what you do? I will give you 1 minute of time. You just take the paper and see whether you can able to write. Clue number 1 for Hell-Vollard-Jelinski's reaction is, it is the only reaction of carboxylic acid, named reaction in carboxylic acid. It is a property of carboxylic acid. It is a property of the carboxylic acid. Okay, it is a reaction in which alpha carbon is halogenated. I have given you 3 clues. It is a reaction of carboxylic acid, clue number 1. Clue number 2, it is property of carboxylic acid. And the third one is, it is the reaction in which the carbon next to COH, that is alpha carbon, is halogenated. Okay, so it is a property of carboxylic acid means it should be of this type, right? This is a carboxylic acid. This is alpha carbon. Yes, next to that functional group, the carbon next to the functional group. So this carbon, this hydrogen is replaced by halogen. So this is RCH2, okay, Cl, COOH. The product is RCH2COH. This carbon is halogenated. Okay, this is not CH2, this is CH, right? Now this is red phosphorus and Cl2. These are the two things that we have to add, red phosphorus and Cl2. So this is halogenated. This is called Hell-Vollard-Jelinski's reaction. Okay. Now coming to Wood's reaction. Try this Wood's reaction. Come on, take the paper, think efficiently. In Wood's reaction, alkyl halide undergo the reaction. Alkyl halide undergo the reaction. Clue number 2, there is some metal used in this process. Metal is used in this process. Okay, this is how you have to recall, right? Alkyl halide, Rx, if it is a general form of writing, if Rx, alkyl halide is represented as Rx, in the presence of sodium, okay, in the presence of sodium metal, right? In ethereal medium, dry ether, ethereal medium, because sodium reacts with water, therefore water should not be avoided. Rx with sodium will give RR. The alkyl group present with the halogen is multiplied by 2 or doubled. That kind of haloalkane is obtained, right? Another product is being sodium oxide. Okay, that is fine. That's fine. This is how it is being. This is being done, right? Okay. So this is the way you have to take up a question and try yourself. This exercise is to be done. You have to take some paper and just recall in any time. You may be using the time when you are going to mess, or sometime you are going or sitting there leisurely, right? Think about one particular named reaction and just try to recall. If you do oftenly, you will definitely remember and you can able to write in the examination well. But this is the exercise to be done sufficient time so that you will remember. Okay, don't think that if one day before the examination you read everything and you will remember everything in the examination. It is not so. Frequency of reading, frequency of recalling will make you comfortable at the end, right? Now, as I told you, we'll go to the mechanism of reaction, mechanism of reactions. So some reactions whose mechanisms are to be understood. Which are that which is asked in the examination? So let us see. So these are nucleophilic substitution reaction. Nucleophilic substitution reaction may be a following SN1 path or SN2 path. Some questions based on that mechanism can be asked, right? Then hydration of alkene to alcohol. Hydration of alkene to get alcohol is a method of preparation of alcohol. Dehydration of alkene, dehydration of alcohol to get alkene. This is alcohol, right? This is alcohol. Alcohol to get alkene, and dehydration of alcohol to get ether. So both are dehydration but occurs at two different temperatures. Okay, so we'll see that all these things, right? Right. Okay. Now coming to the process, the nucleophilic substitution reaction called SN1 reaction. SN1 reaction. Why this is called SN1? Substitution nucleophilic unimolecular. That one stands for unimolecular process. And suppose there is a haloalkane like this, CH3 thrice CBr. This is the given haloalkane. If at all it has to undergo substitution reaction, in substitution reaction, the nucleophile Br minus, nucleophile present here is Br minus. Okay, this will go away and another nucleophile OH comes in, OH. OH minus, another nucleophile OH minus enters in. This is substitution. The compound having a halogen, this goes away as a nucleophile and another better nucleophile enters to the alkyl group. So carbon bonds with another nucleophile. This is substitution reaction. This may occur in two steps like this. The compound may lose this particular nucleophile and the rest of the one is carbocation. A carbocation is being formed. Suppose if the compound is such that on its own it can form a carbocation, this will follow SN1 path. So for following SN1 path, the compound given should be capable of formation of carbocation on its own. I mean with the reagents available for that. Now in the second step, this is the second step, carbocation, the carbon containing positive charge is attacked by this nucleophile. So when nucleophile enters and this is being formed. Now why it is called unimolecular? This is unimolecular because only one compound is involved in the slow step of the mechanism. So I have studied in the chemical kinetics that the reaction in which the reaction which takes place slowly, that if that is being one of the reactions of a compound reaction, then that determines the rate of the reaction. Slow step determines the rate of the reaction. This formation of carbocation is a slow step, very important, slow step. And in this slow step or rate determining step, only one substrate is involved. Therefore, it is unimolecular. It is unimolecular, right? And you can see about the molecule. It is CH3 thrice CBr. It is a tertiary halide. Tertiary halide can form the carbocation more easily. Can tell me why it is so? Why this is more stable? This is stable because of 3 alkyl group which compensate the positive charge over the carbon here. Therefore, this is SN1 path. So few things that you have to remember in SN1 path is this occurs in two steps. One is slow, another is fast. Slow step, there contains only one substrate, that is tertiary halide, right? Tertiary halide. And second step is fast. Therefore, it is SN1 path. From the stereo point of view, let us see in another way. From the stereochemistry point of view, what is the stereochemistry is? Stereochemistry looks at the way the bonding, alignment of the bonding in the three-dimensional space. Carbon is tetrahedral. Whenever it is tetrahedral, the bonds are aligned three-dimensionally, tetrahedrally, right? In order to represent the tetrahedral arrangement, this is the way we write. So the carbon containing halogen is having a solid wedge, representing that some of the one which is bonded to the carbon projects outside the plane, in front of the plane. And there is a dashed wedge, something which is other side of the plane, back side of the plane, back side of this plane. So the molecule, very molecule given, tetrahedral molecule is having three-dimensionally aligned in this way. Now suppose it has to form a carbocation. There will be change in the geometry. Now this carbon has got only 3 alignments. Whenever there is only 3 alignment, so it is a trigonal planar. This is a trigonal planar like this. Okay, this is a trigonal planar. Okay, so trigonal planar stands like this, trigonal planar. If suppose another nucleophile like water or OH minus ion attacks here, there is a chance that OH minus ion from front or it may attack from the back. So there are the 2 alignments, change in the alignment in the compound takes place. Now Br is replaced by OH. Br is replaced by OH. Here also Br is replaced by OH. I mean, after leaving of H from water. Now look at this geometry and this geometry of this. Is there any change in that? Is there any change in this? Look at this. Br is projecting to the right side, but here it is to the left side. And here it is right side. So whenever this is forming carbocation or whenever the compound is following SN1 path, so there is chance that the given compound will be invert its configuration or it will retain its configuration. There are 2 possibilities or the equal possibilities of having both the compounds. So Br is substituted by another nucleophile with inversion in configuration and with retention in configuration, 50% of each. Because whenever triangular planar compound is attacked, triangular planar intermediate is attacked by the 2 reagents from the both sides, then 50% of inverted configuration, 50% of retained configuration will remain. Okay, this has something to do with optically active compounds. So if the given compound is optically active, then you will get 50% of inverted composition and the retained composition. So you will get two kinds of compounds. If this is dextrorotatory, you will get 50% of dextrorotatory and 50% of levorotatory compound. What I mean is, if a compound you start with is dextrorotatory, that means rotating the plane polarized light towards the right, then it ends up in no optical activity. It is because half of the compound will rotate plane polarized towards the left and another half towards the right. Therefore, if mixing of these two compounds 50-50% results in no optical activity, and this process is called racemization. This process is called racemization. So racemization of a process is an internal compensation occurs. It is external compensation occurs when 50% of both kind of compounds are being added. Okay, this is what you have to remember in SN1 path. In SN1 path results in 50% of inverted configuration and 50% of the compound with retained configuration will be there. Now, look at the video so that you may. This is the University of Surrey.
Tertiary halogen alkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that the nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. Tertiary halogenoalkanes. The bulky alkyl groups do not allow attending species to approach the central carbon atom. Consider the reaction between 2-methyl-2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propane-2-ol.
Okay, how this is being formed. So this is the formation of carbocation. Carbocation is being formed by leaving the existing nucleophile. Then another nucleophile gets added up. So energy will be less when there is stability, right? So this is what it explains, right? Thanks to the one video which is being available for showing you. Okay. Now coming to the SN2 path. What is this SN2 path? How this reaction takes place? In SN2 path, the given haloalkane is substituted by the other nucleophile in this way. Both nucleophile, incoming nucleophile, and the one which is outgoing nucleophile of the haloalkane, both will be available. And when the nucleophile which is going, that moves from the one side and the other one enters from the opposite end. Because there is a steric factor. The one which is outgoing and the one which is incoming cannot be from the same axis. Repulsion occurs because both carry negative charge or they are electron-rich species. Now, these two this is an intermediate so formed, right? So the carbon, the other substituents are aligned in the trigonal planar way. The leaving group and the incoming group, the leaving one and the incoming nucleophile, both are at equidistance. This is the intermediate. Now at the end, which is more stable, that is being attracted more towards the carbon. Therefore, bromine completely goes away and this remains, OH remains there. Okay. Now what is the way the stereo part is affected? Stereo part is affected. Suppose if it is a dextrorotatory, bromine is to the right side and OH will be the other side of the compound. OH one will be other side. That means it will be levorotatory. So always the compound inversion in configuration occurs, results whenever it is following SN2 path. Now, how to identify whether it is undergoing SN1 path or SN2 path? Suppose if it is an optically active compound, we can experimentally determine how the stereo part is affected. If a compound forms, dextrorotatory compound forms a levorotatory compound, that means inversion in configuration takes place, then it is following SN2 path. This is the way we generalize, right? So whatever is happened, we try to analyze, probably this is could be happening so. Therefore, that is the way of explaining the mechanism, right? This is the way we explain the mechanism. Now, okay. Now remember that one important thing, SN1 path, SN2 path, two are there. SN1 path and SN2 path. Very, very important thing that you have to remember is tertiary halides undergo SN1 path readily because formation of carbocation is in the intermediate step, right? Carbo is in the step of mechanism. Tertiary halides undergo SN1 path, whereas primary halides will undergo SN2 path. Or in comparison, tertiary halides, secondary halides, primary halides. This is the order of preference for SN1, right? Here, primary greater than secondary, greater than tertiary. This order is followed for SN2 path, right? Now, SN1 path is favored by the polar reagents. Polar reagents, where there is stability of carbocation is more, right? This is the condition for SN1 path. And SN2 path is followed when there is no conjunction or there is no disturbance in the path. Okay. If there is much steric hindrance is there, with much steric hindrance is there, it won't follow SN2 path. It will go SN1 path. Therefore, where there is primary halides, this will preferably undergo SN2 path, right? So this is the important thing. Now, you have to have the more complicated question, which type this is going to, which path this will follow. If this is a haloalkane, if this is the haloalkane, CH3, CH double bond, CH bond, CH2, Cl. Okay. So if this is the one which is now to be chosen, then your primary area to know is whether it is forming stable carbocation, right? So if it is forming stable carbocation, then it follow SN1 path. Remember that this is primary. So you may likely to say that this is, yes, it is following SN2 path readily because it is primary. But remember, this is allylic halide. This is called allylic halide. Allylic halide is having halogen attached to sp3 hybridized carbon. Very next to this, there will be sp2 hybridized carbon. If this condition is there, then it is called allylic halide. What is that? Halogen to be attached to sp3 hybridized carbon, which is next to sp2 hybridized carbon. So if this is the case, then it forms a carbocation. Suppose if Cl goes away as Cl minus, the carbocation so obtained is stabilized by resonance. Therefore, allylic halide is a primary halide, but it undergo SN1 path. Very important point, because wherever there is a deviation like this, and CBS is interested to ask this question there, right? There is another one called benzylic halide. Benzylic halide, this is benzylic carbon and this halogen. This is also primary. Benzylic halide forms benzylic carbocation. Benzylic carbocation like this. So this is also stable because benzene ring is able to stabilize this, okay, by resonance. Therefore, one more point to be remembered is, even though allylic and benzylic halides are primary halides, they form stable carbocation, therefore follow preferably SN1 path. SN1 path. Right. Coming to the next point, let me tell you something about the optically active compounds. Optically active compounds, I talked about dextrorotatory, levorotatory compounds. Yes, dextrorotatory, levorotatory compounds can rotate the plane polarized light. Okay, they have that ability to do that. Such compounds which can rotate the plane polarized light is called optically active compound. So the light from the source, you get to see that it is vibrating in all directions, right? And when it is made to pass through an I call prism or polarizer, it starts vibrating only in one direction of light of propagation. It starts unidirectional like this. And when this made to flow through the tube containing optically active compound, suppose it is an optically active compound solution is kept there, on the path of it rotates the plane polarized light. So this is what the optical activity is. The compound which rotates the plane polarized light is called to be optically active. Here is another diagram. I don't know whether you can able to see properly. This is where the vibration of, you can see the vibration of light, Nicol prism, and this is plane polarized light. In one plane they are there, and it is passing through the tube and it is tilted. You can see that it is tilted by an angle, and for a specific length, 10 centimeter, and the particular concentration, you can write specific rotation of that particular compound. It is constant. If probably biomolecules is over, you know that there is dextrorotatory, levorotatory compounds of glucose, right? Plus or minus, they denote by plus and minus sign. Plus sign tells about dextrorotatory compound, minus sign tells about levorotatory compound. If the compound is, the name is prefixed by plus sign, then it is dextrorotatory compound. If a compound is with prefix minus sign, levorotatory compound. This is how the optically active compound can be identified. With this arrangement, we can able to identify the optically active compounds. Now, in chemistry, how we can able to identify, or in carbon compounds, how we can able to identify? If carbon is having four different constituents, say one is A, another is B, another is C, another is D, four different constituents, all the A, B, C, D are different, then this carbon atom is called to be asymmetric, not symmetrical. It is not having the plane of symmetry, point of symmetry, or line of symmetry. So if all these things are absent, then this is called asymmetric molecule or chiral carbon. This is chiral carbon. The carbon having four different constituents. This kind of compounds are found to be optically active. The carbon containing four different constituents are found to be optically active. Now, when such kind of compounds are kept on the path of plane polarized light, they rotate the plane polarized light. And they will be having the mirror images. The mirror images, okay? So it is easy to write in this way whenever it is given, right? So these are non-superimposable. They are non-superimposable, like left hand and the right hand. They are non-superimposable, right? So like that, they look same, but if you rotate them and try to superpose another, all the groups won't match. Two groups can match. If A and B matches, and then C and D do not match. Okay, so you can exactly take make a ball and stick model, and you can verify this. So this is how the compounds are different. They will be optically active, right? So optically identify the optically active compounds, right? So thing is that carbon should have 4 different constituents, right? Now example. Now this is an example of NCRT question, NCRT textbook. Now among these two, you have to identify which is chiral compound. Chiral compound means carbon having asymmetric. Okay, they have given in green also so that you can easily identify. If these two constituents, this is carbon, HCH3, Br, both are same, therefore it is not chiral. This is not optically active. It has got a plane of symmetry, right? Therefore it is not so. Now, this is so CH3, OH and Br. This is optically active, right? Now look at this molecule. So sometime in bond line formula they gave, okay, in different ways they will give, and you have to identify in proper way. This is carbon, this is carbon, this is carbon. Okay, now look at this. This is carbon, this is CH2, CH3 and CH2, CH3. They are both are alike. If two group substituents are same for the carbon, then it is not called as chiral. This is chiral. This is because methyl group, and this is having 3 carbon atoms, propyl group, and 1 hydroxy group and 1 H. Therefore, this is optically active compound. Now coming to this, you can easily identify CH2 is there here, CH2. Okay, 1 is propyl group and 2H are same. Therefore, it is a chiral, or this is chiral one, because this carbon is having this hydrogen can be written in this way. This is methyl group, this is ethyl group, hydrogen and bromine. See, the way of writing gives a confusion. Therefore, make it clear that the carbon which has 4 different substituents are chiral compounds and they are optically active. Now, in the sample paper about this, what is the question asked? We'll see. This 2023-24 sample paper, it is asked. An organic compound A with the molecular formula C4H9Br. C4H9Br. This is the compound, but there is plus sign. Plus sign. Okay. Undergoes hydrolysis to form plus or minus C4H9OH. Give the structure of A and write the mechanism of the reaction. This is how the question can be asked. Right? So this gives C4 plus or minus, both are there here, plus and minus, both are there. C4H9Br. Okay, what are the clues with us? Plus means dextrorotatory. Plus and minus, if they are both are given, 50% of plus and 50% of minus, that we have to understand. Right? That means racemization occurred. So if the racemization occurred means the compound follow inversion in configuration and retention in configuration, both. In which mechanism this occurs? In SN1 mechanism it occurs. Right, in SN1 mechanism this occurs. So that while writing the mechanism, we have to follow SN1 mechanism. Right, but again structure of A is asked. Another thing is that structure of A is asked. Right, if plus is being written means it should be optically active. An optically active compound means it should have 4 different constituents and it is having 4 carbon atoms. Therefore, how do you guess? How the guess should be made? Okay, this is having Br, the one carbon having Br should have, so okay, one should be H, one can be H and another can be CH3 and another can be CH2CH3. One is methyl group, another is ethyl group attached to the carbon atom, and Br and H. Is it optically active? Yes, it can be optically active. Okay. Okay. Now this, I think this is not being seen. Right. Okay. Then, if this is optically active, then it should undergo in SN1 path. So there is a slow step. There should be a slow step. This is the structure of the compound. While writing the mechanism, you write that in the step, slow step or step 1. So this will form a carbocation CH2CH3 CH, okay, CH3 plus, right? Okay, C4H9Br. It should tally with the molecular formula given. 4 carbon atoms, 3 plus 2, 5, 5 plus 3, 8, 8 plus 1, 9, 9 Br. So this is the compound. So this forms carbocation. And then say that with OH minus ion, okay, so this is fast step. This is fast step, gives inversion in configuration and both. So you may write with a 3-dimensional way, or you may write without that also. Okay. Okay. This is the mechanism. Okay. Writing the structure properly, elucidating the structure properly is important, because it should be an optically active compound. Until you know the knowledge of optically active compound and a chiral carbon which does so you cannot able to do that. So this is the question which is being added. Okay. So such kinds are likely. Such questions are likely. Now, coming to the mechanism, right? Mechanism of another mechanisms. Okay. Another mechanisms that we have, right? What are the other mechanisms which can be asked? So other mechanisms are the 3 other mechanisms which are in the second chapter: alcohols, phenols, and ether. So there is direct questions they ask. Direct questions. Write the mechanism of hydration of alkene. Write the mechanism of hydrogen of alkene. So which are the steps to be followed? It is very simple. You practice a bit. You should surely you will get the marks, because it is having consisting of only 3 steps, and every step is almost similar. Only the point that you have to write, you have to give the account of the flow of electrons, and every molecule with electrons and the plus and minus sign, if it is there, that is to be taken care of. Right. Now, in this mechanism of hydration of alkene is to be taken carbon-carbon double bond, and other things are simply written as a bond. Whatever may be there, attached or substituted. Alkene. So first step is protonation of alkene. Protonation means proton H plus is added. H plus is added to alkene. So this is H3 plus, H3O plus, hydronium ion, right? H plus and H3O plus, both are considered similar, right? Both are considered in the same way, right? You write either H plus or H3O plus, because H plus do not, it is only a proton, it won't exist independently. It will be with water, therefore forms hydronium ion H3O plus. So you may write H plus or H3O plus. From the H3O plus, H plus is given to the carbon, one of the carbon atoms. Okay, so one of the carbon atoms. This particular bond, which is pi bond of alkene, is loosely connected, and this carbon, this electron is shifted to one of the carbon. This is called electromeric effect. This happens in the presence of an acid. So therefore, it is acid catalyzed hydration. It is acid catalyzed hydration. For hydration, even though the water is added, we have to add acid to it. When acid is added, this H plus ion will get attached to that carbon atom, to which this double bond electrons are shifted. So there is a temporary effect that happens with the presence of a reagent. Now the carbon which lost the pi electron, it has get the positive sign. This is the positive sign here. and the one which gains the electron and also binds the H plus ion be neutral. So now the carbon is having positive sign here. This is hydration of alkene. This is protonation of alkene. Proton is added. Then the nucleophilic attack of water on carbocation. So water attacks the carbon which is having positive center. This nucleophiles, nucleus loving, positive charge loving, H2O. H2O in which oxygen containing two pairs of electron, and it acts as a nucleophile. Because of this, it attacks through its oxygen to the positive center. So water gets added. For the oxygen, water gets added. Okay. Now this is water, and there must be one pair of electrons which are there. Since oxygen has given an electron pair to the carbon which was having positive sign, it should be written as positive sign. It should be written with positive sign. And therefore, this is step 2. In step 3, deprotonation to form an alcohol takes place. Deprotonation. In deprotonation, the oxygen having one extra bond out of 3, it has to gain itself to keep a lone pair of electron. This undergo cleavage. You have to show this with arrow mark. And this H plus ion again leaves away. Therefore, this step is called deprotonation. Okay, proton lost. Proton is being given out. Deprotonation. So there are 3 steps of the mechanism. Hydration of alkane. So first step is, in hydration of alkene, is protonation of alkene. Second step is, when protonated, the carbon gets positive charge, then water gets attacked. That is called a nucleophilic attack of water. And the third step is deprotonation. When H2O is added to the carbon containing molecule there, and that H plus ion goes away, leaving the OH as it is. So the alkene, the starting material was alkene, and now the alcohol is being formed. Hydration of alkene gives alcohol. Okay, hydration of alkene gives alcohol. So this is the steps of mechanism. Now look into the another mechanism, very similar one. Dehydration of alcohol. So in dehydration of alcohol, primarily an alcohol, suppose if it is CH3CH2OH, this is an alcohol, right? Dehydration occurs. Dehydration means OH from this carbon and hydrogen from the neighboring carbon goes away, forming CH2 double bond CH2. This is what called as dehydration. The removal of water takes place, therefore it is dehydration. Right. How it exactly occurs? Of course, for dehydration, we use concentrated sulfuric acid. Concentrated sulfuric acid is called as dehydrating agent. Now, how exactly the mechanism is? CH3CH2OH is having, oxygen is having 2 pairs of electron. So this alcohol, using this oxygen having a lone pair, attaches this H plus ion, attaches initially H plus ion from acid. So this is formation of protonated alcohol or protonation. This is also protonation only. There it is protonation of alkene in the first step, and here it is protonation of alcohol. Alcohol is protonated. So when H plus is added, this is the H plus added, and oxygen gets positive sign. You have to mark that positive sign. All right. Then once this is protonated, then there is a cleavage of this bond. There is a cleavage of this bond, giving rise to a carbocation. Okay. So formation of carbocation, it is slowest step and hence the rate determining step of the reaction. This also so. It's a slow step. Okay. You may note down in this way. And then formation of an ethene by elimination of the proton or deprotonation. You can say again the word deprotonation. So this particular one, this carbocation is satisfied by leaving away of this hydrogen, and this bond forms a double bond. Then alkene or ethene is being resulted. Okay. So only the Some similarities are there, and you have to understand that once you understood, and there is no problem of forgetting at all. So definitely you will write in the examination 100% accuracy, right? With 100% accuracy you have to do. And here is the one question, no, here the mechanism is one question which is asked without much twist. Any question can be twisted, but for the mechanism they have to ask in a very straight way. Write the mechanism of dehydration of alcohol. Write the mechanism of dehydration of alcohol at 443 Kelvin. So this happens at higher temperature, little 443 Kelvin. Suppose the same dehydration occurs at 413 Kelvin. Okay, instead of 443 Kelvin at low temperature, then this dehydration results into ether. Dehydration results into ether. So what are the steps of mechanism of this? So the starting material is an alcohol. Dehydration of alcohol we have to do. That occurs in the presence of an acid. The same step, protonated alcohol is being formed, oxygen having positive sign. Now in the second step, the change is, one is protonated alcohol, another is alcohol itself. Second step, one is protonated alcohol, another is alcohol itself. Look at the arrow mark very carefully. When protonated alcohol leaves this bond, this is chance of having positive charge. This positive charge or positive center, this oxygen moves in. This oxygen attaches to this carbon. Therefore, the compound results in this way. Two alkyl groups sandwiched between this, oxygen is sandwiched there and OH is there. Oxygen is having 3 bonds, right? Now, third step is removal of this particular one, and this bond pair will become lone pair. So this bond pair will become lone pair. Already one pair is there here with plus sign, and there is another lone pair. Another one lone pair is there, and another lone pair also results in giving oxygen in this way, and this is an ether. Giving this way, it is an ether. Okay, so what is required here? Only a bit of practice. Okay, so it's a sure question, and you will get 100% marks in this. Don't leave this. Practice a bit is needed. Try to gain that. Right. Now we will move on to reasoning questions. Okay. So the based on mechanism, I think these are the questions which will ask, and there is, as told, that there is no twist or turn in that. Now, another component, very important component that we have to know is reasoning questions. Reasoning questions that are asked, right? So in the reasoning questions, what is to be done is you have to explain in terms of required terms and underline the technical term. Okay, now read the question and see. Boiling point of amines are lower than those of corresponding alcohols or carboxylic acid. So amines. So general representation is RNH2. Okay, so its boiling point is less than alcohols, ROH, or carboxylic acid. Okay, so carboxylic acids are having more. So this is the order of the boiling point, and why it is so, it is asked. Now remember one thing, this is also having hydrogen bonding, this is also forming hydrogen bonding, this is also forming hydrogen bonding. Okay, so hydrogen bonding is not the one word that you should write and forget about other things. It is not so. So you should be able to say very clearly about, even though both are doing hydrogen bonding or all the three are having hydrogen bonding, why this hydrogen bonding is weaker than this? For that reason is this. Here is nitrogen and here is oxygen. Hydrogen and oxygen, which is more electronegative? Nitrogen and oxygen, which is more electronegative? Whenever the boiling point is one of the word there. The key thing that you have to know is it is talking about interparticle force of attraction, right? How the two molecules are held. Two molecules are held. So always two molecules are held by the weak forces. It may be dispersion force or it may be hydrogen bonding. Okay. So dispersion force or van der Waals force of attraction. Okay. It is not covalent bond or ionic bond. So boiling point, whenever they are asking, so it is about the dispersion force or it may be hydrogen bonding. You should talk about that in this way. Now, why this is carboxylic acid is having more than that of alcohol? If this is the question, then carboxylic acid can do more extensive hydrogen bonding because of the two oxygen atom present here. So therefore, the carboxylic acids are relatively having more hydrogen bonding that is possible, right? Now, okay. 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 Okay, fine. Right. So the way that it is being written here, you can see the amines, alcohols, and carboxylic acid, there is a presence of hydrogen bonding underlining. But nitrogen is less electronegative than oxygen. So the intermolecular hydrogen bond which is present in the amines are weaker than the corresponding alcohols and carboxylic acid. So boiling points of the not one technical word you have to write it. This is the best way. And don't allow the examiners to cut your marks by not writing in a proper way. You are knowing the things. Most of you are knowing the things, but somewhere you neglect to write it in a proper way. So proper way of putting it is important in reasoning. Don't think that it is a 1 mark question, therefore only one word that I have to write. It is not so. While the question comes on reasoning, you have to be complete in that, right? Now, phenol is acidic in nature. Phenol is acidic in nature. What is the reason? Why phenol is acidic? Or phenol is acidic than ethyl alcohol? They may give the question like this. Phenol is more acidic than ethyl alcohol, right? So what is the reason? So you may be knowing that phenoxide ion, stability of the phenoxide ion, and so. So you should give an equation. You should give an equation. Phenol C6H5OH gives phenoxide C6H5O minus and H plus. This is phenoxide ion. Then phenoxide ion is more stable due to resonance. Underline the term, underline the sentence. And so phenol is acid. Okay, this is the best way of explanation or the correct way of putting it in. Right. Now this phenol, you have to remember the way of writing its structure and the phenoxide ion. Let me explain you about it. So this is phenol, right? This is phenol. So the phenol is having resonating structure or mesomeric effect. These electrons can be involved, right? And phenoxide ion also. Phenoxide also is having resonance. Okay, this is phenoxide ion. While writing the phenoxide ion, the negative sign comes on oxygen. This is phenoxide ion. This is phenol. This is a neutral compound. So this is the one intermediate that is obtained after deprotonation. After this gives the H plus ion. When it loses its H ion without these electrons, when these electrons stand over here, this becomes phenoxide ion. Now oxygen is having negative charge. Now how it gets stabilized? These electrons are pushed to the carbon, so giving away a double bond character to the oxygen. Now this oxygen having only 2 lone pairs of electron. Okay, so it was having excess. It has given to the benzene ring. So this carbon is having already this bond, pi bond. It pushes to this carbon atom. Okay, so that So this carbon atom is having a pair of electron without bonding and they having negative charge, right? Whereas these bonds will remain as it is. This is one of the resonating structures of phenoxide ion. Again, these electrons will come to form a double bond. Therefore, what happens is this is double bond and these electrons are involved and forming a double bond here, carbon-carbon double bond. These electrons will stand over here. Okay, this double bond remain as it is. Now, oxygen, which was having excess electron due to which it was having negative charge, this negative charge is dispersed to the carbon of the benzene ring. That carbon which is in the benzene ring is in ortho position or in the para position are electron rich or becomes more electron or carry negative charge. They carry negative charge. This is the way of writing. This is the way of writing the intermediates in a proper way, right? Give the account of electrons. That is very, very important thing, right? Now, because of this dispersal of charges, this becomes stable. Phenoxide ion becomes stable. Okay, I usually compare with the tension. Many a time we undergo this kind of chaos in life, or we get tension out of thinking, maybe overthinking or whatever it is. Suppose if the tension is released, then we are safe, right? Stable, we will become more stable. Increase of tension will become more unstable, right? The same way, this phenoxide ion is capable of transferring this tension to the carbon or that carbon to the another one, so that it nowhere it results in at the end the stability increases, right? Okay, another way of looking at it is, okay, this is the right way of explanation. Suppose it is an acid and there will be ionization constant. This is an acid, then it gives H plus ion. And if whenever that is undergoing and giving H plus ion, it is an acid. This is an acid, therefore we write equilibrium constant as ionization constant for acid, Ka value. Ka value of phenol is more than alcohol. The question may be asked in bit different way. Phenoxide is phenol is acidic is one way of asking question. Another way of asking the question, same question, is why Ka value of phenol is more than that of alcohols? The answer would be same, but you should know about what is meant by Ka. Ka is nothing but equilibrium constant value. So you know that whenever equilibrium constant value is larger, then it is acidic character is also more. Okay. So therefore, if Ka value of phenol is more, it is not more, it is more than alcohols, right? So, and it is less than carboxylic acids, right? Alkyl amines are stronger bases than aryl amines. Another popular question. Alkyl amines are more stronger bases. Alkyl amines are represented like this, RNH2, alkyl amines. And aryl amines means this NH2. This is aryl amine. And aniline. Now, these are Levy's bases. What do you mean by Levy's base? A compound which can able to give a pair of electrons is Levy's base. So this is a Levy's base and this is a Levy's base because of ability, it is having a pair of electron and the ability to give the pair of electrons, right? Now, alkyl amines are stronger bases. This can readily give the electron, but this cannot able to give the readily electron. What could be the reason? So whenever you draw the structure, so most of the things will become easy for you. Therefore, I suggest whenever the questions are given, so try with a rough paper or try that by writing the structure. So you will get the answer or you will get the way of thinking, right? See the surrounding of this. Here it is R alkyl group, so which is electron releasing group. It always have the tendency to push the electron, right? So when the pushing tendency is there in the neighbor and it is ready to give its electron easily, that's why it is more basic. But whereas these electrons are involved in conjugation system. It can form a double bond here, and the double bond, suppose, okay. Suppose these electrons are involved in this system, conjugation system, alternate single bond and double bond in that conjugation system, then this cannot be a more basic. This is not having ability to give the electron. Therefore, right way of putting it in is, in alkyl amines, the electron cloud in the nitrogen will be increased due to the presence of alkyl group. Alkyl group, show that arrow mark, so that donation tendency increases. Try to write the pair of electrons above it. Whereas in aryl amines, the electron cloud on the nitrogen is decreasing due to the presence of benzene ring. Benzene ring is an electron withdrawing group. And therefore, alkyl amines are stronger bases. Alkyl amines are stronger bases. This is the right way of writing the answer. Okay. So picturization, drawing the structure, and showing the movement of electrons. These are all the best way of writing the right way in the examination. Best way of writing the examinations. So some books like Oswald books or publications, they will give the copy of answers of the high scoring or high achievers in chemistry, right? So how they have written the answer, how complete this answer is, you have to understand that it is actually the process by which we do and we learn, we understand, or we grow more, we grow our abilities, right? This is the thing. Now you are supposed to write it in this way. So it is easy in this way. If you think about it, this is donation of electron. Who is capable of donating? Who has got regular income, right? One who has got regular income and he is having rich of money and he can donate it, right? So therefore the condition is favorable here. Here this poor fellow is having big family and he has to give all the money to run his family. Then naturally he has less money left out to give, right? Therefore, of course, donation is a tendency. Both are having tendency, but the environment is also important. So this is the environment difference that they have. Therefore, you can remember it, or you can remember that why this is having more basic than this. So instead of asking this thing, they may ask like this: alkyl amines are having more Kb value than aryl amines. Kb value of aryl amines. So the same question can be put in another way in terms of Kb. What is Kb? Kb is ionization constant of base, constant of a base. Okay. Kb and Kb of this is more than Kb of this. So another way of asking the question, let me go to the another level now. Kb is more than this. If Kb of alkyl amines is more than aryl amines, then pKb value is less than that of pKb value of aryl amines. So it is inversely related. If Kb value of this is more, pKb value is less than that of aryl amines. What is this pKb value? Just as that of hydrogen ion and pH value. Same way. Hydrogen ion and negative logarithm of hydrogen ion is called pH. Same way, Kb value, negative logarithm of Kb. Negative logarithm of Kb is called pKb. Okay. So it is also related like this. In the textbooks, pKb values are being given, and you must note these things properly. Okay. Right. Coming to this question, electrophilic substitution, nitration, or halogenation, sulfonation takes place on the benzene when benzene contains an electron donating groups like this. Suppose I will take one of the examples. Here everything is consolidated. So what all the questions which can be asked in the reasoning level are grouped together. If one of the group is attached, they may give specifically this as a one question, and I have combined all this. Whenever these groups are present, suppose if this OH is present here, okay, So if you do nitration or halogenation or sulfonation, it is an electrophilic substitution. Electrophilic substitution that occurs, that takes place. Okay. Halogenation takes place on benzene when benzene takes place an electron donating groups. So this takes place more easily. This, suppose if it is halogenation, it either ortho or para is being seen, right? Halogenation occurs more readily. Why it is occurring more readily is the question, right? Okay, so this halogenation to the nuclear ring, nuclear benzene occurs, or the carbon of the benzene ring, the halogenation occurs. This is called a electrophilic substitution. Okay, the one which is present here will remain here. This is not substituted. Don't think like that. This is nucleophile. This is supposed to be nucleophile if it is going. If it is not undergoing nucleophilic substitution. So the H plus, the H goes away as H plus. Therefore, it is an electrophilic substitution. So electrophilic substitution takes place at ortho and para position when these are there. These are ortho para activating group. Electrophilic substitution takes place at ortho and para position. Now, whenever this is there, they activate the benzene ring for ortho and para position because of plus R effect. This can be donated in the conjugation system, and this kind of donation leads to electron-rich carbon in ortho and para position, right? So I have shown you how to write the resonating structures, right? So you have to write the resonating structure, or you have to put it in this way, right? Okay. So due to the presence of electron donating groups on the benzene, electron cloud increases at ortho and para positions. So the electrophile will attack readily at ortho and para position. Okay. So the electron donating groups, these are electron donating groups. Therefore, it happens so. This is the key word to be written. Now, coming to the another way of looking at it, electrophilic substitution on benzene takes place at meta position when electronic withdrawing group is present. So electron withdrawing group is present. So this is one of the CHO, COH or anode. CHO. Okay. So this is CHO, benzaldehyde. If this is being present, then electrophilic substitution takes place at meta position. What is the reason? It is because this electron is shifted and this electron is shifted, right? This is due to minus R effect, resonance effect, and due to resonance effect, so what is the change in the benzaldehyde? This gets double bond character because of this pi bond, and this oxygen will have 3 lone pairs of electron carrying negative charge. This hydrogen, carbon-hydrogen bond remains as it is. And it is loss of this carbon is at the loss of pi electron, therefore gains a positive charge, and other things being remaining as it is. So this is one resulting structure. Okay. And another structure that can be written is this double bond carbon remain as it is, oxygen having 6 pairs of 6 electrons or 3 pairs of electron will remain, right, having negative charge. Now, to compensate this positive charge, this electrons, pi electrons, will form a double bond, and there is a double bond here, and this will be in this carbon will be having positive sign. Now, among these two, either ortho and para carbon is having positive charge. Now, which carbon is electron rich? Compared to the ortho and para position, meta position is electron rich. Therefore, the center electrophile, okay, electrophile, seeker of electron reaches here. An electrophile is either positively charged, it cannot go here or here. They are get repelled. Therefore, it will come to meta position. Therefore, it is a meta directing. Okay, so this is the way you have to understand. Okay, this is the way that you have to understand, and how to write this answer. Okay, how to write this answer? It is this way. Due to the presence of electron withdrawing group on benzene from resonance structures, the ortho and para position contain positive charge. Could and positive charge cloud. So the electrophile cannot attack on ortho and para position. So it has to attack only meta position having electron cloud. Right? So this is the right explanation. And if you write that structure that I have written, it substantiate, or it is a more perfect way of writing the answer. Right? Haloalkanes are more reactive than haloarenes. Haloalkanes are more reactive than haloarenes. Haloalkanes, this is the way we write here in this way. Okay, and haloarenes, this is haloarene. Okay, now this is more reactive. More reactive means there could be easily this bond can be broken. So that if the bond, what is chemical reaction? It is a breaking of bonds and formation of new bonds. Okay, if this bond is weaker, then it easily undergo reaction very easily. Now this carbon of alkyl group is having a charge plus delta, and this is having minus delta. The carbon halogen bond is polar. Why it is polar? Because of the presence of more electronegative element. Simple. Because of presence of more electronegative element, this bond is having charge. Already they are having then separation. Already the charge separation is there. Okay. Therefore, breaking is easy. Okay, breaking will become easy. But what about this here? Of course, this is also having carbon halogen bond. You may ask me like that, because it is also having carbon halogen bond. This is also having carbon halogen bond. But there is another effect called plus R effect, resonance effect. Electrons are involved forming this bond as double bond. Carbon halogen bond is double bond. Single bond and double bond. This is single bond, polar single bond, and it is a double bond. So double bond is considered to be stronger. Carbon halogen bond is also smaller. Always double bond is smaller than single bond. So it is stronger. Therefore, haloalkanes are more reactive than haloarenes. In haloarenes, the halogen which is present on the benzene ring donates its lone pair of electrons to the benzene ring, which results in the resonance. So resonance leads to stability and less reactivity. Whereas the haloarenes, no resonance results, less stable, more reactive. It is less stable, more reactive. This is the way you have to understand. Ketones are less reactive towards nucleophilic addition reaction than aldehydes. Why? Ketones are less reactive towards nucleophilic addition reactions. So nucleophilic addition reactions, ketones are also having this carbonyl group, and aldehydes are also having this. Ketones are having this plus delta and minus delta. Carbon having plus delta and minus delta. This is because of the electronegativity difference that as I told you. But ketone is having an alkyl group, and here also an alkyl group. Maybe different alkyl groups or same alkyl group, whatever. They are having two alkyl groups, ketones. Ketone C double bond O is in between two alkyl groups. But in aldehyde, one is alkyl group and another is hydrogen. Right? Now these electron releasing groups, alkyl groups are considered to be electron releasing groups. These electron releasing groups compensate the positive charge on the carbon. They decreases the positive charge. Hence, this reactivity reduces. But whereas here in the aldehyde, there is only one alkyl group. Therefore, it has less effect of such kind. Therefore, it is more reactive. So you have to write these two particularly, and then explain the meaning of this, right? Okay. Nucleophilic addition reaction takes place when nucleophile will add to the positively charged carbon. In ketones, are two alkyl groups are there. You can see two alkyl groups. Okay, electron donating groups are there, and the partial positive charge which is present in the carbon is neutralized by the alkyl groups which are electron donating groups. Okay, partially neutralized, may not be completely. The aldehyde, the partial positive charge which is present in the carbon is partially neutralized by only the alkyl group, one alkyl group. It is also partially done, but it is less than that of this. Therefore, ketones are less reactive than aldehydes. So this is the way you have to put in your answers. Compare the acidic strengths of these two. Oh, important. Acidic strength. Okay. Now look at this. This is COOH, something like this, COOH. Okay. This is carboxylic acid, something about carboxylic acid. Okay. So in particular, if you draw everything, this is alkyl group this side and COOH other side. Now, if COOH gives away H plus ion, then these electrons will remain here. This is called carboxylate ion. So this oxygen gains negative charge. A carboxylate ion is stabilized by resonance again. How? These electrons are being given out and these electrons are standing over the other oxygen, giving rise to the carbon with double bond oxygen and a single bond oxygen here. Okay. Now this negative charge is shifted to this oxygen. So what we find here, the negative charge is passed to one oxygen to another oxygen in the resonating structures. Okay. So resulting into the movement of electron cloud over the carbon, which is electron rich. So the two oxygen which are more electronegative, they try to retain the negative charge. Therefore, it is more stable. It is more stable than phenoxide ion. Because phenoxide ion, the negative charge is dispersed to less electronegative carbon atom of the benzene ring. But here, the oxygen retains the negative charge. Therefore, it is more stable. Carboxylation, why carboxylic acids are more stronger acid than phenols, then this is the answer for that. So carboxylic acid is more stronger acid because the negative charge of the oxygen is on the oxygen, which is more electronegative in case of carboxylate ion. Now suppose the alkyl group is present here, and along with that there is one atom like chlorine. This chlorine is electron withdrawing group. It is minus psi effect. It has minus psi effect. Chlorine, whenever it pulls its electron, pulls the shared electron, so that it drags the electron from that carbon. So this carbon is already having negative charge, and if somebody pushes this electron cloud towards it, it will be happy or it is stabilized. So this carboxylate ion is stabilized if there is an electron withdrawing group, EWG. This is the way it explains. In the book, it is being given EWG, electron withdrawing group, attached to the carbon having that carboxylate ion, then the stability of the carboxylate ion will become more. So electron withdrawing groups increases, electron donating group decreases the acidity. Now coming to this question, there is chlorine, fluorine, and iodine. Three are there. Now, which is more electronegative? This can withdraw the electron more powerfully. Now, I think you have already come to the answer. Can you tell me? Can you recall? Okay. So fluoroacetic acid, chloroacetic acid, iodoacetic acid. Fluorine is more electronegative than chlorine. Chlorine is more electronegative than iodine. Therefore, this is the order. I hope it is understood, right? Okay. Now, so that is the thing that we have to write. Now compare the basic structures, basic strengths of the following. Basic strengths of the following. Okay. Now, this is another way of asking a question. This is alkylamine, this is arylamine. As I told you, if you remember, you can able to tell me, or now it becomes easy for you. If the questions are asked in a different way also, you can able to answer it well. If I write like this, I think you will be feeling more comfortable. If I write like this, so electrons are donated to the benzene ring. Electrons of the methyl group is having plus I effect, pushes the electron cloud towards nitrogen. So this is more basic than ammonia. Ammonia is having neither electron donating or electron withdrawing, right? Therefore, this is the order of it, right? The basic strength is like this: CH3NH2 greater than NH3 and CH5NH2. So CH3NH2, CH3 is electron donating group. Okay, this is the same thing that is being told, right? Now coming to this. Formaldehyde gives Kenny-Rose reaction, whereas acetaldehyde does not. Formaldehyde and acetaldehyde. So let us recall this. Formaldehyde is HCHO, right? HCHO. Okay, you can write like this. HCHO is formaldehyde. Acetaldehyde is CH3CHO. This is acetaldehyde. Okay, formaldehyde and acetaldehyde. So formaldehyde undergo Kenny-Rose reaction. Kenny-Rose reaction is a disproportionate reaction, occurs in the presence of a base like NaOH and KOH, and this happens only if the alpha hydrogen is not present. If alpha hydrogen is present, then it undergo aldol condensation, right? So this is the functional group. The next to that is the carbon, and this is having alpha hydrogen. This contains alpha hydrogen. This is alpha carbon. But there is no carbon at all here. This is not alpha hydrogen. That hydrogen should be linked to the carbon. So this is not the alpha hydrogen, but therefore this formaldehyde undergo Kenny-Rose reaction. Formaldehyde does not contain alpha hydrogen. The compounds which does not contain alpha hydrogen undergoes Kenny-Rose reaction. So this is the way that you have to write the answer. Phenyl methyl ether, anisole, reacts with HI to give phenol and methyl iodide, but not iodobenzene and methyl alcohol. Probably a question seems to be very difficult, but when you draw this, I think you can able to say the answer. So those who can able to draw the structures correctly, phenyl methyl ether, phenyl methyl ether, this is an ether, phenyl methyl ether will give, okay, so will give, anisole will give phenol, one is phenol, okay, and another one is methyl iodide. Okay, this happens, they have given as this happens, but doesn't give, it doesn't give iodobenzene. This won't give iodobenzene. Okay, iodobenzene and methyl alcohol. This won't occur. Why this won't occur? This is a very important question in ether. Definite one question. If the ether something is asked, means it will be asked in this way. Okay. So now this is a reaction with, okay, reacts with HI. HI is a strong acid. This H hydrogen ion attacks the oxygen. Okay, this takes a pair of electron, this pair of electron, and forms H, and giving the oxygen a plus sign. Now either this bond will break or this bond will break, depending upon which is weak, right? Now anisole is also having plus R effect, therefore this carbon oxygen bond is having double bond character. This is stronger because of the plus R effect. Anisole OCH3 when is there, it forms such kind of compound. Therefore this is stronger. Therefore this is not likely to be undergo cleavage. This undergo cleavage. Therefore this is broken. Therefore you are going to get this product. Okay, so this is how you can able to explain, right? HI is a strong acid and which will cleave the oxygen and the alkyl bond, because of the oxygen and phenyl bond is low reactive. Okay, this is the way that is being given, right? Unlike phenols, alcohols are easily protonated. Alcohols are easily protonated, okay, whereas phenols do not undergo protonation very easily. Okay, this is a question, because alkyl group there is electron donating group, but whereas this donation of this electron becomes easy, whereas these electrons are involved in conjugation system, therefore it is not easily protonated. So that is the way of answering. So everything in the structure, if you elucidate the structure properly, you can able to say the answer, right? Carboxylic acid do not give the characteristic reaction of carbonyl group. This is another thing. Carbonyl group is C double bond O, that is aldehyde or a ketone, and this is having plus delta and minus delta sign. The charge separation is like this. But whereas I told you in carboxylate ion, this carbon is having negative charge. So carboxylate ion is having this negative charge over the carbon, but this carbon is having positive charge in aldehydes and ketones. Therefore, it is different than that of carboxylic acid is different than aldehydes or ketone. So that is the answer, right? So delocalized, and that is the way that is being answered. Chloroacetic acid is having higher Ka value than acetic acid. Chloroacetic acid, chlorine is electron withdrawing group. The same question asked in different way, right? Okay, why control of pH? This is the last question. Why control of pH during the addition of ammonia derivatives to aldehydes and ketones needed? So pH value is essential to be controlled because the amines and ammonia and ammonia derivatives are basic in nature. If you provide the strong acidic character as the medium, then these bases react with the medium acid, not the reactant. Okay, it won't go for reacting with aldehyde or ketone. If it is basic medium, if you provide, then that protonation, if donation or electrophilic substitution reaction won't take place. Therefore, this nucleophilic substitution won't take place. Therefore, this is not a this is to be done with the pH 4 to 7. That is the ideal pH for having this kind of reaction. So electron withdrawing group on carboxylic acid increases the acidic strength, and the chloroacetic acid, chlorine is withdrawing. Okay, okay, of course, this is the what I am doing. Okay, right. Okay, so we will do the checking of the order of the property in the tomorrow's class. Just in the beginning of the class, I will ask you a few questions on what the property that we have learned or reasoning that you have given, whether you can able to apply to the real situation. So that is that such kind of questions, order of the property also will be asked. And thank you for your listening or active participation. And we'll see in the evening today regarding the further of the reactions, right? Thank you. I will close this. Close this.